Hello viewers, you are welcome to the fifth video on the necessary and sufficient conditions for Laplace transform. So in this video we are going to consider another case of functions of an exponential order. But the only thing about this one is that the function we're going to consider is a mixture of polynomial and exponential. So we need to study this one again, and then of course, as usual, we are still going to use the same things we'll be very familiar with, the procedure. So we follow it for the last time, then we will proceed. So thank you very much for watching. So let's proceed. So in summary, we can just put the whole things like a question, and the question is saying that if we are to consider the function f of t is equal to t raised to the power 3, which is a polynomial for that 3, multiplied by exponential t. If you are to consider this, can we really say that f of t have a Laplace transform? That's the first question. And we're asked to justify our answer by analyzing the behavior of f of t as t grows large. We really need to recall, the behavior required for the Laplace transform, okay? Because we are very familiar with the fact that the Laplace transform exists if and only if the function f of t, it must satisfy the exponential order condition. What is the condition? The condition is absolute value of f of t must be less than or equals to m multiplied by exponential gamma of t. So remember this statement, there are three things. Number one, m must be a constant that is greater than 0, because we need it to define the boundedness of the function f of t. Number two, exponential gamma of t. Gamma can be 0 and it must be greater than 0. So it's either gamma is 0 or it's greater than 0. Gamma can never be a negative value. And the t must be a variable greater than 0. Okay? So these conditions, they actually ensures the fact that the f of t does not grow faster than exponential gamma of t as our t becomes a bigger number. Which is a necessary condition for exponential minus stf of t to decay and the Laplace transform to converge. So let's focus now on the function f of t, which is the multiplication, but it's a product of two functions. But the first thing we need to look at is the fact that exponential t, it dominates the growth of f of t, because we're talking about exponential function, and like I've said earlier that you guys should plot the graph of exponential 5t and plot the graph of exponential minus 5t. You will notice that in the case of 5t, the number will be growing so large that you may not be able to control them. So now here, the term exponential t, it dominates the growth. So whatever that happens to e of t, we multiply, we predict what f of t will be as t is growing large. Because if you look at it, that of polynomial, the growth of polynomial cannot be compared to the growth of exponential. So that is why here the statement is presented as follow, that the term exponential t, it dominates the growth of f of t because exponential functions grow faster than polynomial functions as t grows large. So considering the nature of exponential t multiplying with the polynomial, it's an indicator that the function of t we are studying, which is t raised to the power 3 exponential t, is going to grow faster than any m exponential gamma of t for any finite m and gamma. So based on that, we can actually conclude that the function of t does not satisfy the exponential order condition. It's very obvious, and the major reason is because of that exponential t, not because of the polynomial t raised to the power 3. So for the integral to converge, as we can see, if we are to find the Laplace transform of f of t, which will eventually give us 0 to infinity t raised to the power 3, then exponential 1 minus x in the bracket multiplied by t dt. So for this to converge, for this particular integral to converge, it means that that exponential must be a negative value. And for that to be a very negative value, it means that 1 minus x must be less than 0. So if 1 minus x is less than 0, what does it mean? It means that x must be greater than 1. And that is the only condition for us to find the Laplace transform of that function. That is the only condition that is very necessary. Because if x is less than 1, that integral will diverge. And in other words, 1 minus x, if it is greater than 0. If 1 minus x is greater than 0, then definitely we are going to have integral 0 to infinity t raised to power 3, then exponential of positive value. And if you have exponential of positive value, then that is an indicator that the integral will not converge. It will definitely diverge. However, even if x is greater than 1, the polynomial term, which is t raised to power 3, it grows unboundedly. Yes. And then exponential 1 minus x multiplied by t cannot decay fast enough to contradict this growth. Thus, the integral will definitely diverge. So based on this, we can now see now that although t raised to power 3 to it contributes, but its contribution cannot be compared to that of exponential t. Yes, so it's the one that will make that we can use to predict that for this one, although x must be greater than 1, but even if x is greater than 1, what about t raised to power 3? Because t raised to power 3 as t is growing large, you can plot a graph. Just consider like 5 values of t. When t is 1, when t is 10, when t is 30, when t is 100, when t is 1000. What can you say about t raised to power 3? You notice that the polynomial 2 will also be growing large. So compare this one with the video 4. In video 4, you see that we have only one function, which is exponential 2t. Aha. And with that, we concluded that the Laplace will exist if and only if x is greater than 2. But for this one, we have exponential t multiplied by t raised to power 3. And we follow the same procedure, and we realize that the Laplace transform will exist if x is greater than 1. But there is another problem again. That t raised to power 3 will also contribute another issue, because the function will grow unboundedly because of the polynomial. So for this, we can definitely be rest assured that the integrals will diverge. Okay, ladies and gentlemen, we can now conclude. And the conclusion is that the function we are studying, which is f of t equals to t raised to power 3 exponential t, this function does not have a Laplace transform. It does not have a Laplace transform because there are two reasons. Number one, this function t raised to power 3 exponential t, it grows faster than any exponential of the form exponential gamma t, which indeed violates the exponential order condition. Number two, as the function t grows large, the integrand, which is exponential minus stf of t, which we've seen clearly now that by the time you replace f of t with t raised to power 3 exponential t, it will give us that expression on the screen. It does not decay fast enough, causing the Laplace transform integral to diverge. So lastly, this example highlights how the behavior of f of t as t grows large and how it directly influences the existence of the Laplace transform. Functions growing too rapidly, they may never satisfy the necessary decay condition, and their transformations do not exist. So we are going to end this video here, and we can see clearly now that there are some conditions we could actually use to know if the Laplace transform of any function exists or not, and if it exists, on what interval of x. Thank you very much for watching. Bye.